Two-way slabs are elements in where the members are designed to support loads through bending in two orthogonal directions, where the ratio of the long to the short side of a slab panel is less than or equal to 2. The most common types of two-way slabs are flat plate, where a two-way concrete slab is supported directly on columns. Flat slabs are two-way concrete slabs supported directly on columns where the slab is thickened around the columns. Those thickened portions are called drop panels. Two-way beam-supported slabs are two-way concrete slabs with column-line beams on all four sides of a panel. Two-way joist slabs consist of evenly spaced concrete joists spanning in both directions and a reinforced concrete slab cast integrally with the joists. Solid slab sections are provided around the columns mainly to provide two-way shear resistance. Two-way slabs must have sufficient thickness so all applicable strength and serviceability requirements are satisfied. If we look at the cross-sectional view of the slab, the minimum slab thickness can be determined by making sure the deflection limits in ACI 24.2.2 are met. Alternatively, according to the type of the two-way slabs and whether they are connected to an edge beam or not, the minimum thickness can be determined from section 8.3.1 of ACI. Where stirrups are used as part of the two-way shear resistance at critical sections in a two-way slab, the minimum slab thickness requirements in ACI 22.6.7.1 must be satisfied, where D is the distance from the extreme compression fiber to the centroid of the longitudinal tension reinforcement. For two-way slabs, an average D can be approximated by H minus 1.25 inches. Thus, the slab thickness H must then meet the following requirements. For flat plates, the minimum slab thickness can be determined according to the following table. The minimum slab thickness will depend on the steel grade and whether or not the exterior panels have edge beams and must be greater than or equal to 5 inches. Ln is the clear distance between the support faces in the long direction. Exterior panels are those at the edge of the slab, and interior panels are those surrounded by columns that lie inside the slab and not on the edges of the slab. The thickness of a flat plate is usually controlled by the serviceability requirements in Table 5.2 for span lengths in the range of 15 to 25 feet and live loads less than 40 pounds per square foot. Otherwise, two-way shear requirements will control. In that case, we can choose preliminary slab thickness using this graph, where QU is the factored uniformly distributed load, including the self-weight of the slab. The thickness assumed to calculate the weight of the slab can be taken from Table 5.2. A is the tributary area of the column in question, and C1 is the width of the square edge column with an area of C1 squared. And then, by matching the load to the respective line in the graph based on the ratio of the tributary and column areas, we can obtain the ratio of D to the column width. Approximating the slab thickness as D plus 1.25 as previously done will then give us the required preliminary slab thickness for two-way shear. For flat slabs, the minimum slab thickness can be determined according to the following table. The following dimensional requirements for the drop panel should be met in order to use the table. Like for the plates, Ln is the clear distance between the support faces in the long direction. The minimum thickness determined by this table must be greater than or equal to 4 inches. For two-way beam-supported slabs, the minimum slab thickness can be determined according to the following table, where alpha FM is the average value of alpha F for all beams on the edges of the panel, and alpha F is the ratio of flexural stiffness of the beam section to the flexural stiffness of a width of slab bounded laterally by central lines of adjacent panels, if any, on each side of the beam. The effective beam and slab sections for the computation of the flexural stiffnesses can be seen in these figures for edge and interior beams. Beta is the ratio of long to short clear spans, and Ln is the longer clear span similar to the previously shown slab types. In edge panels with edge beams where the stiffness ratio alpha F is less than 0.8, the minimum determined slab thickness by the equations in Table 5.6 must be increased by 10%. For two-way joist slabs, the standard form dimensions are given in the following table. For design, a two-way joist is considered to be a flat slab with the solid heads at the column acting as drop panels. The cross-section is transformed into an equivalent section of uniform thickness TE, with the same width as the actual section. The equivalent thickness is determined by setting the moment of inertia of the equivalent section equal to the gross moment of inertia of the actual joist section. Then, the equivalent thickness should satisfy the requirements of Table 5.4 for serviceability requirements for minimum depth. For purposes of analysis, two-way slab panels which are bounded by columns, beams, or wall center lines on all sides are permitted to be divided into column strips and middle strips. The width of the strips depend on the spans L1 and L2. Where L1 is the length of the span in the direction moments are being determined measured from center to center of supports. L2 is the length of the span perpendicular to it. A portion of the moment transferred from the slab to the column is due to flexure and the other is due to eccentric shear. To determine the portion due to flexure in terms of the factored slab moment, a factor gamma F is multiplied by the factored slab moment. It depends on the critical section dimensions shown B1 and B2. The determined moment and the effective slab width B slab are used to determine the required flexural reinforcement in the slab. In slabs with drop panels or shear caps, the effective slab width changes as follows, where L is the width of the drop-down panel. The two-way shear critical sections in flat plates and flat slabs are shown as follows. In flat plates, the critical section lies a distance d/2 away from the face of the supports. In flat slabs, there are two critical sections, one in the panel that is a distance d2/2 from the face of the support, and one in the slab that is a distance d1/2 from the face of the drop panel. In the case of a shear cap, there are also two critical sections, one in the panel that is a distance d2/2 from the face of the support, and one in the slab that is a distance d1/2 from the face of the shear cap. In the case of columns with circular capitals, with and without drop panels, the critical sections are determined as shown. The critical section can be 3 or 4-sided depending on the distance of the column from the slab edge. If the column is closer than half the perpendicular column width plus the distance to the reinforcement from the extreme compression fiber, the critical section will be 3-sided, otherwise it will be 4-sided. The critical section for two-way shear in slabs with circular columns has a square shape with the following dimensions. Critical sections in slabs reinforced with stirrups or shear studs are shown as follows. The sections are polygon-shaped and there are two critical sections per column. Gamma V MSC is the fraction of the factored slab moment resisted by the column due to eccentricity of shear. This moment is applied at the centroid of the critical section and produce the assumed factored shear stresses shown. The total factored shear stresses on faces AB and CD of this figure of the critical section can be determined by the following equations. An example calculation of the critical section properties of rectangular columns is shown. The direct design method is an approximate analysis method that gives reasonable conservative values of bending moments at the critical sections for two-way slabs subjected to gravity loads. It is done by dividing the slab into design strips and is applicable only when the following limitations are met. There must be a minimum of 3 panels in each direction. The columns must be in line with a maximum offset of L2 divided by 10. The applied load should be uniformly distributed, with the unfactored live load being less than or equal to twice the unfactored dead load. The length of the panels should not differ by more than 1/3 in each direction. The ratio of the long to the short length of the panel should be between 1:1 and 2:1. If any of these conditions is not met, the direct analysis method cannot be used, and alternative methods like finite elements should be used to determine the internal forces in the critical sections. Analysis of the slab is performed in each direction independently, and 100% of the total gravity load must be carried in each direction. The first step in determining the factored bending moments in a design strip using the direct design method is to determine the total factored moment in each span, where QU is the total factored uniformly distributed gravity load. Ln is the clear span in the direction of analysis. Any non-rectangular column shape is converted to rectangular for the sake of determination of Ln. L2 is the length of the span in the direction perpendicular to L1, measured center to center of supports. The second step is to distribute the calculated moment into positive and negative bending moments in each span. The spans are either end spans or interior spans. This is done by multiplying m0 by the coefficients in the tables. Afterwards, these moments are distributed in the design strip to the column strips and middle strips. Using the following percentages for the column strips, the percentages for the middle strips will also be known. Beta T is the ratio of the torsional stiffness of an edge beam to the flexural stiffness of a slab width equal to the beam length. The larger of these two C values should be used for the calculation. If there are no edge beams, beta T is 0. And if there are no beams between supports, alpha F is equal to 0. Thus, the following values are examples of percentages of the moment m0 in the column strips for a flat plate slab without edge beams and without beams spanning between supports. The following is a summary for the total moments and their distribution to the column and middle strips at the critical section for all the discussed types of two-way slabs. The moments transferred to the supporting columns or walls by two adjacent slabs where one is longer than the other is shown. L1 and L1 prime are the center-to-center spans of the longer and the shorter slab respectively. Ln and Ln prime are the clear spans of the longer and shorter slab respectively. QLU is the factored live load on the longer span. QDU and QDU prime are the factored dead load on the longer and shorter spans respectively. The moment is then distributed to the top and bottom column or wall in direct relation to the member stiffnesses. Beams must be designed to resist applicable tributary factored shear forces due to the factored loads. The tributary areas for beams in a two-way beam supported system are shown. The gray tributary area applies to the interior beam that spans between columns A and B, where the ratio of alpha F1 L2 over L1 exceeds or equal 1. The beams carry all the shear and the shear around the columns is 0. Whenever that is not the case, the portion of the shear resisted by the beams is the ratio itself, and the remaining must be resisted by the slab around the column. These shear stresses are calculated as shown previously through the following equations. Having said all that, these conditions must be met such that the two-way slab is considered safe when it comes to the strength requirements. In the next video, we will look into the calculation of the bending and shear strengths of a two-way slab and how to determine the required flexural and shear reinforcements. In addition, we are going to look at the recommended reinforcement details as well as other reinforcement requirements set by ACI. Don't forget to like and subscribe and turn on the notification bell. Thank you for watching.